Hello students. In the last lectures, we had seen the basic phenomenon photoelectric effect. Then the experimental setup for the same we had seen, and by means of that experimental setup, number of observations from the experiment on the photoelectric effect we had discussed. Now let's proceed the chapter. First of all, before moving ahead, let's see what are the failure of wave theory to explain the observations from experiments on photoelectric effect. That means the observations we had discussed from the experiment on photoelectric effect, it could not explained on the basis of the wave theory of light. First of all, the observations could not explained by the wave theory of electromagnetic radiation. Okay, as over here wave theory is to be given by means of the electromagnetic radiation, as we had discussed the same in the introduction part, that the wavelength, frequency, okay, amplitude, time period, these are the basic features, basic properties of the electromagnetic radiation there, of a wave there. So on the basis of the wave theory of light, all the observations which had been made from the experiment of the photoelectric effect cannot be explained. Then what are the failures? That is, let's discuss about it. According to wave theory, first of all, the metal surface absorbs all incident energy continuously. We had seen in the photoelectric effect, as soon as the radiation of suitable frequency incident on material, electrons are emitted from the surface of the metal. Here, according to the wave theory of light, it is to be given when the electromagnetic radiation is to be incident on any material, it will absorb all energy continuously, and hence the electrons which are near the surface, it will absorb all the energy there, which followed that the metal surface require reasonable time to accumulate sufficient energy, as all the electrons are absorbing the incident energy, so it will take time, and hence the process of photoelectric effect, in which as soon as the incident radiation will be given to the metal, electrons are emitted from its surface. But here the radiation, when it is to be given to the metal, the energy will be absorbed by the surface and all the electrons, and hence the reasonable time is required to knock off the electrons. That means the time will be takes place to emit the electron from the metallic surface. It is to be given as per the wave theory of light. This argument was contradictory to the observation. One of the observation we had seen that photoelectric effect is an instantaneous process. That means as soon as the suitable frequency radiation incident on the metal, electrons are emitted from its surface without any time lag. But here, according to the wave theory, the reasonable time, that must be, it may be nearly equal to few minutes to hours. Okay, so the metal surface will require reasonable time to accumulate the sufficient energy, because of which the electrons will be emitted from the surface. Now the next observation is to be given as per the wave theory of light, that the greater intensity, if it is to be given on the metal, so that the more will be the incident energy. That means if the intensity of the incident radiation is greater, the large amount of the energy is to be incident, and hence the expected time which is required to knock off the electrons will be less over there. Okay, this is to be given as per the wave theory of light. On the another hand, it is to be given as per the wave theory of light, if the intensity is small, that means for the small incident intensity, the energy that must be incident on unit area in unit time, it will be small, and hence because of it, it will take longer time to knock off the electrons. Okay, here two observations from the wave theory of light is given. If greater intensity is to be incident on the material, the time required to knock off the electron will be less, and if the small intensity is to be incident on the material surface, then longer time is to be required to emit the electron from the surface. Okay, but we had seen in the photoelectric effect that the photoelectric effect, the phenomenon is an instantaneous process. As soon as the suitable frequency radiation is to be incident on the material, the electrons are emitted from the surface without taking any required time. The process happens very quickly. It takes the time around 10 raised to minus 9 seconds. So these arguments were contradictory to the observations, that those observations that is to be observed from the experiments on the photoelectric effect, and hence here we can say that the wave theory of light is fail to explain the observations from the experiments on photoelectric effect. Now let us try to estimate the time that will be required for the emission of electrons from the metal surface and for the photocurrent to start. And because of that, here we need to define the term which is said to be a work function of the metal. As we know that metals have free electrons, and metals are good conductors of heat and electricity. So these electrons which are free, they are moving inside the metal, but otherwise they cannot escape from the surface. Okay, electrons are free, and hence inside the metal they are moving here and there, but over here they cannot escape from the metal surface. The electrons can be escaped if and only if the sufficient energy is to be supplied. Okay, when the sufficient energy is supplied to the electrons, then only it is possible that the electrons are escaped from the metal surface. and hence over here the minimum amount of energy must be provided to an electron to pull those electrons from the metal from its surface, and hence that minimum amount of energy is called as work function of the metal. And hence we can define the work function of the metal is the minimum energy required to free electron from a given surface is called photoelectric work function. It is denoted by a letter phi 0 of the material of the surface. For example, let us assume that it is our metal. Okay, the electrons are there inside the metal and they are freely moving here and there. When the minimum amount of energy is to be incident on the material, so that over here due to that minimum amount of energy which is to be required for the electron to just escape from its metallic surface. Okay, that means how much energy we have to supply to this material so that the electrons from the surface of the material will leave it and hence it will escape from the metal. So that amount of energy is said to be a work function of the metal. Now the work function, obviously it depends on the properties of the metal or the material or nature of its surface. Okay, now the values of the work function of metals are generally expressed in unit of energy which is called as electron volt. Over here the some values of the work function for common metals which is to be used for this purpose is given in this table. As the work function depends on the properties of the metal and the nature of its surface, so for a given material the value of the work function which is measured in electron volt is constant. That means if we are using potassium, so 2.3 electron volt is enough for the potassium, that when 2.3 electron volt energy is given to the potassium, electrons from the surface of the potassium will be emitted out. But again the work function for different material will be different. As you remember, we had discussed in the case of the threshold frequency of the material used for the photoelectric effect. The value of the threshold frequency for a particular metal used is same. Okay, but it will be different for different materials. For example, whatever the threshold frequency of the potassium is there, it will be same for all potassium, but the value of that threshold frequency will be different from the threshold frequency of the sodium. Similarly, here the work function for certain metals which are given over here as you can see in this table. Okay, so for the certain metals the work function in the electron volt is given. So these values will be same and will be different for different materials. For sodium, 2.4 electron volt energy is supplied and hence the electrons from the surface of the sodium will be emitted. As already we have discussed this graph in which the material of the emitter plate is changed there, and it is to be observed that for different metals, as the nature is same, so the slope of such straight lines were the same, but the intercept of this frequency for the metal A that we are getting as phi 0 for the metal B as it is to be given as phi 0 dash. So these intercepts on the frequency and stopping potential, it will be different. Okay, so what is this phi 0 over here? As we have discussed that in this topic, there is a minimum amount of energy must be required so that the electrons are emitting from the surface of the material, and that minimum energy is called as work function. And also we had seen that the work function for a certain material is same but will be different for different material. So it is given over here in this graph that this phi 0 is nothing but the work function of the metal A, and hence we have to apply the certain amount of energy so that the electrons will be emitting from its surface, and hence the photoelectric current will be flowing. For the metal A, it is to be given at phi 0. So for the metal A, the value of the work function phi 0 will be same. But as we are changing the material, so for the material B, the value of the work function will be different. It is to be given as phi 0 dash. Okay, it is different than the metal A. So this phi 0 dash is the amount of energy which is to be required to liberate the electron from the metallic surface. And hence over here for the metal B, the work function is to be given as phi 0 dash. So it is to be understand that there must be minimum amount of energy to be given to the emitter plate, and hence by using that amount of energy, the electrons will leave the surface of the material, and that amount of energy is called as work function. So here we come to know that the value of the work function for a certain material is same, but it is different from different material. Now, secondly, it was given as per the wave theory of light that the larger intensity implies larger energy, and hence within the less time the electrons are expected to be emitted with the larger kinetic energy. Means when the intensity of the incident radiation is more, as per the wave theory of light, electrons will be emitted in a less time with larger kinetic energy. But the observation that we had seen in the photoelectric effect, it showed that the maximum kinetic energy did not depend on intensity of incident radiation. It depends on frequency of incident radiation. And according to wave theory, the frequency of incident radiation has no role in determining the kinetic energy of photoelectrons. So this is again one of the contradictory statement given by the wave theory, that the maximum kinetic energy depends on intensity of incident radiation. It does not depend on the frequency of incident radiation, whereas we had seen in the photoelectric effect, the maximum kinetic energy we are getting by means of the frequency. Intensity will not play any role for determining the kinetic energy of emitted photoelectrons. But as per the wave theory of light, frequency of incident radiation has no role in determining the kinetic energy of photoelectrons. Over here, wave theory expected that photoelectrons to be emitted for any frequency, whatever will be the intensity. The frequency of the photoelectrons determined by using the wave theory of light if the intensity of radiation is large enough. But the observations we had seen that for a given metal surface, over here some characteristic cutoff frequency which we named as threshold frequency nu 0. It must be exist as per the photoelectric effect. Okay. Below this threshold frequency, there is no photoelectrons were emitted. However, the intensity of the incident radiation was. And photoelectrons were always emitted if incident frequency nu was greater than threshold frequency nu 0, even if the intensity was low. So these are the contradictory found in the wave theory, and hence based on this contradictory, the wave theory could not explain the observations that has been determined from the experiments and the observations that has been takes place from the experiments on photoelectric effect. After discussing the failure of wave theory, let's proceed to the next part of the chapter, that is Einstein's postulate of quantization of energy and the photoelectric equation. Now, first of all, the Planck's hypothesis of energy quantization was given based on which the black body radiation can be explained, and hence the same hypothesis was extended by Einstein in 1905, and it must be there for all types of electromagnetic radiation. Over here, Einstein proposed that under certain conditions, light behaves as a particle. It is very important aspect for the dual nature of light, that as per the Einstein's, under certain condition, he proposed that light behaves as a particle and its energy is released or absorbed in bundles, and those is to be named as quanta. Over here, the energy of light he named as photon, and these photons are nothing but the released or absorbed energy in the form of bundle, or we can say like the shower of particles or quanta. Further, these things is to be named as energy of light is to be named as photon. Okay, and the energy of these photons are to be given as, but this equation, E is equal to h nu, where nu is the frequency of incident radiation, h is the constant which is to be defined by the Planck in his model to explain the black body radiation, and as it is a constant, so the Planck's constant value is to be given, as you can see, h, the Planck's constant value is also given over here, that is around 6.626 into 10 raised to minus 34 joule second. Okay, we can convert the same into the electron volt second there. Over here, the relation E is equals to h nu. This relation is there between the particle-like property, that is the energy E, and the wave-like property, that is the frequency nu. That means this relation, which is also called as Einstein's relation. Over here, the Einstein's relation gives the relationship between the particle-like nature and wave-like nature of light. And hence, this Einstein's relation holds good for entire electromagnetic spectrum. It says that the energy of electromagnetic radiation is directly proportional to the frequency and inversely proportional to the wavelength, as the relationship between the frequency and wavelength, as they are inversely proportional to each other. Okay, so here it is to be concluded that the high frequency radiation means high energy radiation. Alternatively, the short wavelength radiation means high energy radiation there. So this relation is to be given known as Einstein's relation, E is equals to h nu, and it is to be extended by the Einstein by using the Planck's quantum theory. So far we have studied the phenomenon photoelectric effect, and to observe that photoelectric effect, we had seen the experimental setup for the same, and by using the same experiment, observations we have taken from the experiment on photoelectric effect, and next it is to be found that the wave theory of light could not explain those observations. The wave theory of light has failed to explain the observations from experiments on photoelectric effect because the contradictions has been found in the wave theory. And one more very important phenomenon we come to know, that is called as the work function of the metal. We had studied about the same, and after that we had seen the Einstein's relation. Over here, by using the Planck's quantum theory, Einstein extended the hypothesis and given his relation, which is E is equals to h nu, which is a very important part of this chapter. Here, the dual nature of light we will study, as based on this Einstein's postulate of quantization of energy. the light behaves as a particle, and further equation will be given by the Einsteins, which is said to be a photoelectric equation. So we will see next time in the next lecture the photoelectric equation given by the Einsteins, which is also called as the Einstein's photoelectric equation, and based on the Einstein's postulate of quantization of energy and Einstein's photoelectric equation, the observations that we have studied already from the experiment on the photoelectric effect. So those observations can be explained, it can be proved by using the Einstein's postulate of quantization of energy and Einstein's photoelectric equation. So inshallah, we will see all these things next time in the next lecture. Thank you.